So once you know terms, once you know the details at the top, we're going to get into sample problems. After the sample problems, you have some practice problems you can work on. So the first thing we did is free body diagrams with these systems of different blocks. So it says 2 blocks, and they give you one of 4 kilograms, the second one of 6 kilograms. They are connected by an inextensible string, so it doesn't stretch, basically is what they're telling you. For this one, it says that a vertical force of 50 newtons is being applied to it. Pay attention to the way that they describe this, because what you'll notice is it says that it's being applied to which block? Well, it's being applied to the second block, right? And so when you draw these systems, you want to make sure that you are drawing them correctly. So even though it gave it to you in one order, it's actually telling you that force is being applied to the 6 kilogram. So if I were to write this one's going to be my M2 there. All right, because that vertical force is being applied right there. And then I want to draw the rest of that. So I have a second block that is actually the M1 because of how they described that vertical force, okay? The vertical force there. Now, the first thing they want me to calculate is the acceleration. Remember, your force equals your mass times your acceleration, all right? And so for the whole system, you have basically 2 forces acting on it. You have the applied force that's pulling it up, and you have the force of gravity, which is pulling it down. Those are the 2 forces acting on this system, right? We have a vertical force pulling it up that's applied. That means someone's holding it of some sort. Something is holding it with that type of force. And then we have gravity that's pulling down. Yes, there is tension in between the blocks, but those cancel each other out for the overall system. All right, for the overall system acceleration, you just have to worry about the applied force and the total gravitational force. And that's going to equal the total mass of the system times that acceleration that you're trying to solve for. And so we're going to fill those in. The applied force is the one that they give me. That's 50 newtons. The gravitational force, well, that's going to be the total mass. The total mass here is 10. Times gravity, negative 9.81. Gravity's acceleration there. All right? Those forces are working against each other. That is going to equal the total mass. Again, 10 times that acceleration that we are trying to solve for. So when you solve for that, we're just going to add up that left side and divide by 10. We're going to check our significant digits here. We have 2, 2, and 3, so we're going to say 2 significant digits. So go ahead and calculate the acceleration of this particular system. So the second portion of this says calculate the tension, and really if I calculate one of the tensions, I have all of the tension because the tensions are the same, all right? And so if I look at these systems, you can really do either the top block or the bottom block. It doesn't matter because the tension's going to be the same. So if I look at this, I personally would look at maybe the bottom block because it's fewer things acting on it. On this bottom block, if I were to draw this free body, I have tension pulling up and I have gravity pulling down. And those are the only forces acting on that, correct? Tension pulling up and gravity pulling down on it. So if I take the tension and I add the gravity for that one little block, then I get the mass times the acceleration for that block. Right? Remember, the acceleration for the individual blocks and the acceleration for the systems are the same. So the only thing I don't know here is the tension. So I'm going to fill everything in that I do know and calculate what I don't know. I have tension plus the force of gravity. Well, the force of gravity is the mass of that second block, which is 4, times the gravitational pull, negative 9.81. And that's going to equal the mass of that block. Again, that's 4 times the acceleration that we just figured out, which is negative 4.8 meters per second squared. So I'm just going to multiply those, and I'm going to add across that force of gravity. So you should get 20.04, but we're talking two significant digits. 20 newtons, you can either put a decimal at the end of that 20, or you can underline that 0 to let me know that is your significant digit there. But those are your two significant digits. The next one. All right, so this is two blocks. They're connected by a light, inextensible string. It's not stretching over an ideal pulley. Calculate the acceleration of the system and the tension on the string. Remember, for this one, again, you want to draw free body diagrams, and I think my instructions on your quiz says draw free body diagrams here. But we have one block. We have another block. All right. Remember, you need to establish your positive and negative, because if I were to take those two blocks on the string and straighten them out, right, then it makes sense. But when they're hanging like this, it looks like one's gravity is pulling down and one gravity is pulling up, right? But that's not actually the case. It just means if you were to flip that around, you would see that positive and negative actually going in the same direction. But when they're hanging like this, your positive and negatives are two different directions. So I usually use my bigger box because to me that makes more sense, all right? Which means I usually say for my bigger box, I usually say, well, that's going to be my positive direction and that's going to be my negative direction. Which means for my smaller box, that would be my negative direction and that would be my positive direction. If you were to flip those around, you would see they're actually going the same. All right, but when they're hanging, it looks opposite like this, which means when I apply gravity to these, the one that says positive down, I'm going to use a positive 9.81 for him, and the one that says negative, I'm going to use a negative 9.81 for him. All right, does everybody see that? So, all right, so it says two blocks are on a pulley. They're connected by a string. Calculate the acceleration. So this is a little bit different. So for these, I set them up as two separate ones. You don't really want to do the entire group to find your acceleration because they're working against each other, not together, all right? And so I would take the first one, maybe the small one here, and I would say, well, the total force acting on it, well, that's the force of gravity that's acting on it, plus the tension of that string, all right? And that's going to equal its mass times its acceleration. And of course, the acceleration is going to be the same, but that's what we're going to solve for. All right, so then force of gravity on this smaller box, right, is going to be the smaller box's mass times the gravity acceleration plus that tension equals its mass times acceleration that we don't know. All right, so if I solve for t here, I'm going to get this 5.00a. You can say minus. It's technically going to end up a plus because it's minus a negative, but we'll just subtract it over. That's its tension, okay? Does everybody see that? That is its tension right there. Let's look at the second box. Let's look at this guy, all right? The things acting on this, again, is going to be that force of gravity plus that tension, all right? And we'll talk about what that tension means, right? This is a second tension, all right? A second tension. That is going to equal the mass of that box times its acceleration, which again will be the same acceleration. Here, the force of gravity for this guy is going to be its mass times gravity acceleration, except now we're going to use a positive 9.81 there. All right, now we're going to use a positive 9.81. The tension 2. So tension 1 and tension 2 are almost equal, right? Except one thing. They're opposite of each other, okay? So I can replace that tension 2. I'm going to have to negate everything over here when I move it, all right? So I'm still going to write the tension 2 for now, but when I set it up to make it equal to the other guy, I have to negate everything because they're working this way, right? As all tensions. One's pulling this way, one's pulling that way. And so it's going to be its mass, again, times that acceleration that we don't know, which is what we're solving for here. All right. Now that we have that, we are going to just solve here for the T2. That's going to be 10A minus 10 times my 9.81. All right. Now, I almost can set them equal to each other, right? I have a T and a T2. So I can say that T should equal the negation of the T2. So we're going to negate that whole thing. And now I'm solving for one variable. All right, so simplify this. This is a negative times a negative. So I have 5a plus 5.00 times 9.81 over here. Distribute, negative 10a plus 10 times 9.81. And now I'm ready to solve. Variables to one side, numbers to the other, and then divide, right? So I'm going to move this over there. I'm going to move this over here, and then I'm going to solve. All right, so add the 10 over. We have 15a. Subtract the 5 over. We basically have 5 times 9.81 using distribution, right? And then divide by that 15 to solve. So my acceleration, this guy was, it was only 2 significant digits. Was it 2? Nope, 3. 1, 2, 3. 3 significant digits. So we have 3.27 meters per second squared. To find the tension, this equals the tension right here. We can literally just plug it back in, right? So my tension is going to be just plug it back in now that you know the acceleration. 3.27 plus 5 times 9.81. We're going to solve for tension just plugging it back in. Tension is going to be 65.4 newtons there. And you have answered both of those questions. A block of mass of 8 kilograms slides down a frictionless incline that makes an angle of 30 degrees with the horizontal. Calculate the normal force acting on the block and the acceleration of the block. All right, so we have this right angle situation here. They have given us a block that is sitting on it. Oh, nope, I don't want a triangle anymore. I want a block. We have a block sitting on it. We're going to turn him so that he's correctly sitting on. There we go. All right, so we have this block here. They've given us the incline. The incline is 30 degrees. All right, so the first thing they ask is normal force. So remember, the force of gravity is always going to be straight down. Force of gravity is going to be straight down towards the earth. It doesn't matter how that guy is sitting. We're going to break up the force of gravity into 2 forces. We're going to break it up into the force that runs perpendicular to what it's sitting on, and we're going to break it up into the one that's parallel to what it is sitting on, all right? If I find the perpendicular force, I have found the normal force, all right? The normal force is always also perpendicular, just in the opposite direction, all right? So the first side of the triangle that I'm trying to solve for is that one because it will equal that normal force that I need. All right, remember, the fun thing here is that this little teeny angle at the top of that triangle will always equal the angle of the incline. So when I'm trying to solve, I'm going to draw this little triangle out here. when I'm trying to solve for this right here, I have an angle of 30 degrees and I know the force of gravity. How do I know the force of gravity? Well, because the force of gravity is always mass times 9.81. And I'm going to use a positive 9.81 here because I'm trying to find normal force who's going to be working against gravity. Okay? Right? So, with SOHCAHTOA, I have the hypotenuse. My hypotenuse is always going to be my regular old force of gravity. We're just going to negate it. We're going to go the opposite direction. We're not going to use negative 9.81. We're going to use positive because it's working against gravity. My adjacent side is going to be what we're solving for, right? My adjacent side is going to be equal to that normal force. Equal to that normal force. So I have an angle measure. I'm looking for an adjacent side. I have the hypotenuse. Which trig function deals with adjacent and hypotenuse? Cosine. All right, so the cosine then of my angle should equal that adjacent side divided by that hypotenuse. That's how it's always going to work out for the normal force here. So we're going to fill in, obviously multiply the normal force, the force of gravity over. So the normal force is going to equal the force of gravity. That is going to be 8 times 9.81 times the cosine of that angle incline. So go ahead and calculate what the normal force is on this. 3 significant digits here. So if you plug it straight in, you should get 67 point, no, oh, because you rounded. Is that what you're saying? So yeah, when you round, there we go. I was wondering why we were getting different numbers here. Yeah, so if you round up the 9, it's going to round up the 8 and make that a 0 there. Okay. All right, now we have to use the parallel movement here. The one that's working parallel. Well, the one that's working parallel is going to be my opposite side. So we have a couple things. We're going to say the force that's going this way is going to equal the mass times the acceleration. So the first one we were just calculating the force, right? Calculating the force, what is it? Now we're saying calculate acceleration, which means we need the force of the gravity that's working parallel in that x position here. And we are going to then say that is going to equal the mass times the acceleration, which is what we're solving for. All right. It's frictionless. All right. So it's going to be the only force acting on it. Gravity is the only force acting on it. This is a frictionless incline at this point. So we're going to do exactly the same thing. We're going to say, well, the opposite side should equal the force of the gravity x over the force normal here. All right. And so once again, we're going to do our trig function here. I'm going to do it this way. So we have this. So the sine then, because we're using opposite, the sine of 30, if we multiply by the force of gravity now in the x position, we should get the, if we multiply by, the normal force, then we should get that. So we're going to say, start again with that. That's my force of gravity. Times the sine of 30, right? That's going to give me that x position. All right? That's going to give me that x position. So now we're using this, right? But we don't just want to stop at force. If they just said, what's the force working parallel? We would say, got it, we're done. They're asking for acceleration. So the force of that parallel should equal the mass. We already know the mass. Acceleration is what we're solving for, times acceleration. So the gravity pull to the x is going to equal the mass of that object times the acceleration. When they ask for normal, we just solve for force and we stopped because it's not moving up and down on that incline. There is no acceleration. It's equal and opposite. It's not floating or sinking into it. The acceleration is only going to happen in the parallel position. All right? So we're going to use our cosine to find our normal force, and we're going to stop. But for our acceleration, we're going to use the incline force, the gravitational pull in the x position, which is sine this way. All right? And we're going to divide it by the mass because we're doing one more step here because it is possible it's sliding up and down that. It's not possible that it's floating above it. There is no applied force, right? So solve for that. Multiply to get that parallel force and then divide by the mass to get your acceleration. All right, divide by the mass here to get your acceleration. 4.91. Let's look at the next one. A person with a mass of 70 kilograms stand on a scale in an elevator. Calculate the apparent weight of the person when the elevator accelerates upward. Remember, we have two things. They're working against each other, right? So we're going to say, well, the force is going to be what I'm solving for. The apparent force, we'll just say apparent because it's not actual, right? Is going to be the acceleration of that times that mass that we have, mass times acceleration. And then we're going to subtract the acceleration of gravity times that mass. Remember, if it's accelerating upward while gravity's pulling downward, it's going to look like it weighs more than it does, right? It's going to look like it weighs more than it does. So then we just add them up pretty much. What do you get when you say 2 times 70 minus a negative 9.81 times 70? So 5 and 6 deal with static and kinetic friction. The first one wants us to find the static and kinetic friction. All right. 10 kilogram block is sitting on a horizontal surface. The force of 30 newtons is required to start the block. Once it's moving, 20 newtons is required to keep it going. So they've given us the max of the static force, which should equal that coefficient that we're looking for times the force that is normally on that block. So for us, the max force is what started it moving. That should equal that little coefficient we're solving for times the normal force. Well, they gave us the mass of the force, not the weight. So we have to take the mass that they gave us times the force of gravity. You don't have to negate it. We understand it's just directional, so you don't have to negate that. So you're just basically going to take that 30 and divide by the 10 times 9.81 or by 98.1. So your static coefficient should be something like that. Well, when we want it to keep moving, it doesn't take as much force. It only took 20 newtons of force to keep it moving. That is the kinetic friction. And that's going to be our coefficient of our kinetic friction times, again, that normal force. So now we're going to say it only takes 20 newtons to keep it moving. We're solving for this unknown coefficient, but we're going to multiply by that same force that was acting on it to begin with, which means we're going to take 20 and divide by the 98.1. And you should get that your kinetic coefficient then is 0.204. So now we're saying the force of my friction is going to equal the coefficient of my friction times my normal force. All right? Force of friction is the coefficient times the normal force, whichever one you're looking for. So then the flip side of that is, what if you know those coefficients and you're trying to figure out, can I move it? Like in the next one, 8 kilogram block is placed on a horizontal surface. The coefficients, they give them to us. You apply a horizontal force of 35 newtons. Will the block move? Well, static. We're going to solve for the static first. So the static friction max is what we're going to solve for. We're going to take the static friction coefficient. We're going to multiply it by the normal force. That's its weight times gravity. You're just multiplying straight across. Your coefficient times your mass times your acceleration of gravity. And you get that the total frictional force, what is working against you, is 33.197. So the question is then, is what I am applying greater than what it has given back? And it is. My applying of 35 is bigger than the 33.2. Yes, this block will move. Yes, it will.
If we do.
The next thing is, what's the acceleration? Well, the acceleration is the total forces acting on it, which is the applied force, how you're pushing it, minus now that kinetic friction. Friction's working against me, right? Me pushing, kinetic friction's now working against me. All right? And that's going to equal the mass of the total object times that acceleration that we're solving for. Applied force they gave me. You are applying a force of 35.0 newtons. The kinetic friction is now going to be the kinetic coefficient, 0.345, times the normal force. Again, it's mass times gravity. So we're going to subtract those two. That will equal the total mass times that acceleration guy that we're solving for. So you're going to subtract 35 minus all that multiplication there. And then you're going to divide that. So you should get approximately 7.9244. You don't have to write it all out. You're going to divide that mass over. But we only want 3 significant digits here. And this does have a unit. Remember, your coefficients don't have units. They're just coefficients. Acceleration and force have units. Force is a unit of newtons, acceleration meters per second squared.